Good morning. Today we get together to discuss some subjects which are related to the three first chapters that you read in my book on Hermitian Quantum Mechanics. And I would like to focus today about the questions, what are these resonance in natures that I'm talking about. It's related to chapter 2 in the book. And then I will discuss a little bit things that are related to chapter 3, where we discussed different type of methods that can be used in Hermitian quantum mechanics to calculate the resonances, to see their fingerprints in nature, and to calculate their energies, and their decay rates, and the lifetimes, and etc. So we'll not get to the details. We'll not go over these three chapters, but I would like to focus today about what are resonances in natures. And I would like to start with shape type. Resonances. The name indicates on their sources. Their sources are because of the shape of the potential. So let's do it explicitly in the beginning, for tunneling resonance. Then it's clear to all that the resonance phenomena associated with the shape of the potential. So let's assume that we have a potential that looks like this. This is x, and this is v of x. It's clear that if we will put here a wall, and we think about particle in a box, we know that there are infinite number of bound states. But if, on the other hand, we'll erase this and we'll change the potential to be like this, namely without this barrier, no barrier, so now our potential looks like this, then we know that this remains as bound states, and so this is bound state number 1, this is states number 2, this is states number 3. The question is, what's happened to these states? We cannot refer to them like tunneling because they don't support it by barrier from the surrounding, but we later will discuss about the other type of resonances, and we'll show that these are actually also become to be metastable states. So how they look, this is a no node, one node, two nodes. In the moment that we return to this situation when we have a barrier, we know what's happened. This bound states that was before bound states tunneling through the barrier, and here we have oscillations. And this has one node and oscillates more. And this one has two nodes and oscillates even more. Question number 1 is why I say that the amplitude of the states, which is the no node, the ground state here, has a smaller amplitude outside in the continuum. The continuum starts from here, it's clear. In this problem, there is no bound states really in this potential. But why I say that this has smaller amplitude than this, and this has smaller amplitude than this? The reason based on semi-classical theory that says and show that the transition probability at this energy from here to here is related to an exponent. I'm not going to teach semi-classical theory. That the exponent is of an integral from this point to the points of this square root of this area. And this area is large, so the probability to get from here to here is small. In this energy, the probability to get from this point to this point is proportional to an exponent in the power of minus the integral of square root of this area. And from here, square root of this area. Do you remember? Rings bell? So this is what we know. In the book, we have shown that, roughly speaking, the resonance decay rate is associated with the ratio between the amplitude outside and inside, roughly speaking. Flux normalization, energy normalization, you should read it there. Now, this behavior explains, I think, quite clearly why we refer to these states of the resonances, stunning resonances, as bound states in the continuum. They are not true bound states, but almost bound states. If the barrier is large, they look really like bound states. They are not bound states, they are quasi-bound states. They have a large amplitude inside. This to distinguish between, I hope that we'll see the blue, from the continuum solutions that are in between. Let's assume that we want to look at this continuum states. It's a non-resonant state because it's an energy, a continuum starts from here, in between these two, for example. How these functions looks like? It has a very small amplitude here and a very large amplitude here. So the non-tunneling resonances, or resonance tunneling, I don't know, tunneling resonances, have large amplitude outside and small amplitude in the interaction region. The resonances, which so-called bound states in the continuum, has large amplitude inside and small amplitude outside. And this is the reason that in the book I describe the stabilization method, which is related to box quantization. That you introduce here a box, and you solve this, and then you get quasi-continuum. You have the discrete spectrum, depends on the size of the box. And when you plot of the energy of this function of the size of the box, these states that are tunneling resonances, that bound state in the continuum, they have a large amplitude inside the well. Very small amplitude outside. And therefore, they are not much affected by the cutting or increasing the size of the box. And therefore, roughly speaking, if you look at state number 1, for example, it looks like this. If the box is large enough, and then I increase it more and more and more, it changes, of course. But I do it like a straight line, assuming that the changes in the amplitude here are related to the amplitude inside are so small that in the scale of your calculation, you hardly see it. Of course, you will see it because it's not really straight line, it's a slope, but this is a schematic picture. On the other hand, if you look at the continuum functions alone, it's clear that they have a large amplitude outside and very small amplitude inside. They are strongly affected by the size of the box. And as you go to larger and larger box, you get closer to 0 if I take this threshold energy is 0 point. So they change like this. And as you increase the size of the box, the density of the states become to be larger and larger. So you'll say you get now, more solutions that decay. So they come to be more and more dense, and more solutions that decay as you increase the size of the box. Now we have the non-crossing rule. Non-crossing rule implies and says it's I cannot say it proved, but it was formulated by von Neumann and by Edward Teller, and says that if you have states that have the same symmetry, it's unlikely them to cross if you change one variable. And because of this, you see here in the calculation avoided crossings. So this avoided crossing is a change from the bound states to the continuum states. So this is bound state to the continuum. This is pure continuum that I describe. And any avoided crossing describes a transition from this to this. So whenever we do such stabilization picture, this is the size of the box, but it can be used as a scaling the coordinates sometimes if the potential is analytical. Then whenever we see such avoided crossing, we know that they are related to resonance phenomena. If we have this is one, here we have another one is the two. So again, we'll see this picture here. I'm sorry, this is not here. So we see something like this, etc. And this is actually the resonance wave function. This, the avoided crossing, is the region that when you have the transition from the bound state in the continuum to the continuum. So this is a prototype of tunneling resonances. Now, I said to show it in nature. So this, of course, can be produced in quantum wells, for example, by semiconductors to take layers and layers. Each one of them has a different layer. It can be done. It can be related to optics. We'll discuss it in a moment later. That it's remind actually also what can be done in waveguides. I'll talk about it later a little bit. So these are the tunneling. Now the question is if it's must to be tunneling. If we have in this one-dimensional one, we have a shape-type resonances, but not clearly, not transitions through barriers. Barriers. Not transition through barriers. Can we have? The answer is yes. In the book and also in the previous lectures, I described a potential that looks like this. This was our step potential. This was 0, and this was minus V0. And I've proved to you here that if this V0 is going to infinity, we get particle in a box spectrum, exactly like it was infinity, like I told you before. Now, if V0 is not infinity, this comes to be resonances, metastable states. Again, bounce in the continuum. This state looks like this and oscillates. This is come to be like this and oscillates, etc. In a way, I think that here you'll see something, a nice phenomena that I don't remember that if I really ever studied it carefully. That I think intuitively that the amplitude outside of this one will be larger than this one. So it will be just the opposite. And the reason that I'm saying it is because that now these bound states embedded in the continuum for this part. And the density of states in the continuum are smaller, are proportional to square root of 1 of the energy. So if we look at the energy of this particle, this is the energy of the particle which get out, and this is the energy of this. 1 over square root of this is larger than 1 square root of this energy. As the denominator becomes to be larger, the density of states come to be smaller. So it's not enough that we have penetration into the continuum. We need to have density of states there that will trap our particles. Otherwise, we don't have some, the particle will not be trapped in the continuum. It's like to say that that we play with a ball that we hit to the wall, and if there is no wall on the other side, there is nobody that will hit it. Now we know that usually it's going through and not reflected, but in this case it's the opposite from this intuition, because the shape type resonances associate not necessarily with barriers, not necessarily with transitions through barriers. It's actually related to the sharpness of the change in the potential. It doesn't have to be discontinuous as I do it here. It can be continuous. And it can be a nice project to try to replace this sharpness by a function like tangent hyperbolic that change abruptly around this point. And we have a parameter that we control it to be more sharper and more sharper and more sharper, and to see how the lifetime of these resonances are affected, how this amplitude, all these pictures that I tell you in Hermitian quantum mechanics, how it's affected by the sharpness of the edges of the potential. And you see, this I do it like to be smooth, not to emphasize about being piecewise potentials, which implies that they are not analytical one. So the non-analyticity is not a must to get this type of resonances. It helps, but it's not a must. And this is why these are, I can erase here and put exclamation mark to say these are really resonances. They have a very short lifetime. The amplitude outside are very large, but can be distinguished from the continuum functions that have a large amplitude outside. So all these functions have a larger amplitude inside than outside, but the ratio between these amplitudes come to be smaller and smaller, but still can be distinguished in non-Hermitian quantum mechanics, even mathematically exact, from the other states in the continuum. Any questions? So I want now to show to you a physical example. I say that my purpose is to give you physical examples right now. So I want to speak about the spectrum of diatomic molecule and I think about raw vibrational spectrum is the spectrum that you solve its H psi equal to E psi when H is a diatomic molecule. Let's assume this molecule is AB. And we use the Born-Oppenheim Hamiltonian, and we want to solve this. And when we solve it, we write the Hamiltonian as minus h bar divided by 2 mu. And let's take it to be, I'm sorry that, OK, I'll finish and then I say, like this, I make some transformation to make this Jacobian to be like this, not 1 over r. And here, minus oh, sorry. Sorry. Plus VR. So yeah. And the V of R is obtained from the electron structure calculation. This is actually the electronic energy function of the distance between the two atoms. And if we make a plot of it, we get, when it's bound state, we get it to be like this. When we make it to be such that this is 0, this is the R0 when the molecule is bound. So this is the bond length of the molecule. This is the dissociation energy. We know we can prove that for neutral molecule, this is related to the R/6. This is called is known as van der Waals forces, the attractive forces. And if usually people use the Lennard-Jones potential to describe this. No, it depends. This is Lennard-Jones in order to make sure that this is behave correctly. And as you said, more often, at least in our group, that we are using the Morse potential, and the Morse potential is D1 minus E minus alpha R minus R0 square. When R is equal to R0, this is 0, so this is why we put here to be minus D. When D is the dissociation energy. Okay, and why we are using this? It's doesn't have the correct asymptotical forces on energies. The reason is that this potential can be solved analytically. The Schroeder equation, without this term, without the rotation, can be solved analytically. Now, because of this separation, it's possible to prove that when we write the exact wave function as a product of spherical harmonics and radial functions, that here we get to the h bar square j times j plus 1, when j is equal from 0, 1, 2, etc. And these are the rotations. Or rotational quantum number. Quantum numbers. Mu is the reduced mass of the molecule, so it's m mass of A, mass of B, mass of A plus mass of B. And this is the Hamiltonian that we want to solve. So we have a diatomic molecule. This is A and this is B. The center of mass can be here, and this is what we solve. Okay? Now, how we can see from here that we have shape-type resonances. So let's make the plot now. When we put here V effective of R, which depends on J. So this is our V effective J of R. So for J equal to 0, we know how it looks. It looks like this. We put this to be 0. And if we solve it, we get here bound states. You may ask if there are resonances from the type that I told you before above, because there is no barrier here. Now it depends, and we can prove actually that in the case of Morse, there are no resonances above. Because? Decay resonance, because it goes too smooth. Now, if you take now J equal to some high numbers, it depends on the molecule, it comes to be like this. This is J, call it 0. I choose a specific number, depends on the molecule, such that I get still a well below the threshold, but also a barrier above. What's happened now? Of course, all these states move to here. So now, this, maybe I will raise this. So now the new one will be here, and here, and here, let's assume. So these two are what? Are bound state. And this is the resonance, the tunneling. It's 0, 1, 2 nodes, so it's look like this, and here it oscillates. Because what I told you about this sharpness of the potential, here is something interesting. This barrier, even if it's tiny, may introduce resonances above. Maybe we'll have here, above this, here in the continuum, we get also solutions that have large amplitude in this region, above the barrier. So even a slightly small barrier, because it makes the potential to be more abrupt. You can see, the moment that you introduce the barrier, we don't have introduced tunneling, but also we change the potential to change quite dramatically, or quite fast, or quite rapidly, from attractive to repulsive. And this by itself introduces resonances, metastable states. So when we solve it, we solve the Schrödinger equation, get the vibration spectrum for each one of the quantum rotational states J. And if you do it like this, and you do all this stabilization, you will see really, even in Hermitian quantum mechanics, that for large enough J, this disappears. If you take very large J, it can be like this, namely no bound state at all. And for sufficiently large, you will get something like this. So as you go to highly rotational excited states, all the bound states will disappear, and you will get this situation. You may assume that from this, that if you take a molecule and put it in rotationally excited to highly rotational excited, take a microwaves, which is the energy spacing between the rotations. And if you take it into a microwave, and the microwave will be strong enough, and or better to say, homogeneously walk sufficiently long, and if the system is quantum, no external perturbation, you keep the system to be coherent, then in time you're excited to a very highly excited state. Even if the intensity of the microwave is not so large, you have probability to happen. And then this molecule that are excited to highly rotational excited states, what would happen to them? They will break. They will dissociate. So this is actually, if you want, mathematical indication to a phenomena that absorption of microwaves coherently for sufficiently long time, and to keep the system isolated from the environment, because otherwise you don't have quantum mechanics applicable in such a simple way. So if you take material wave mechanics, remember it's not wave mechanics for waves, it's not light, but it's matter waves, it's Schrödinger equation. As long as the Schrödinger equation can be such that you can isolate your molecule from the surrounding, then definitely, if you excite the molecule to high enough J, the molecule will dissociate. And how long it takes depends on the shape of this potential, usually on this size of the barriers. The resonances that I told to you here definitely are extremely short, have a very extremely short lifetime. And actually this one will be very hard to see, and actually you will not see them by instabilization plots. Why I said it's hard to see, and why I said that you will not see. Because in order to see them, you need to solve numerically the energies in the box extremely accurate. So if you have good computer and no round F errors, and you calculate it exactly, you get the exact spectrum of the molecule inside a box, then if you will do that stabilization calculation, calculate the energy as function of the box size, I assure you that if you will calculate not the energies as function of the box size, but the high order derivatives of the energy with respect to the box as function of the box, then even this resonance will pops out. You'll see structure, and again, look at my book. In my book, I chose on purpose to study all these phenomena for a potential, one-dimensional potential step type potential, as I discussed before, that doesn't have a barrier. Because in order to emphasize on the fact that you don't need to have a barriers in order to see sharp resonances or resonances at all, and even very long lifetime resonances. So this is describe the spectrum of the atomic molecule raw vibration states. Okay? Now, I want to give you another example. The other example will be atoms in DC field, in static field. Okay? So the Hamiltonian, in such a case, will be the Hamiltonian of field-free atom. Now we are speaking about electrons, plus or minus, depends on the sign of the electric field. Epsilon 0 is the strength of the static field, charge of the electron, and here all the electrons, call it J maybe, call it Z, J, this is the coordinates of the electron. When we assume that the direction J is the direction, the coordinate J is the direction of the static field. The static field is along one direction, and we take this direction as our Z coordinate. And this is, and of course, this is depends on X and Y and Z. And X, Y, and Z, I don't put the indexes, but we have many electrons, of course, and it doesn't have to be one electron system. What's happened then? So let's illustrate it for just the one-dimensional potential. That this is, I'm doing it because this you can solve it numerically. And let's assume that you describe the atom by such a potential. This is V, call it effective, X, and this is X. And this is a minus, take it to be in atomic units. Let's take it to be like this. This is called, if you want, let's put here some Z effective is actually the effective charge, this electron, positive charge to this electron field. So this can be more general. And this is a small parameter. And this is called soft Coulombic. Soft Coulombic potential. Actually, it's very interesting that if you, in the one dimension, if you take A to be 0, then you get a situation when the electron cannot go from one side of the nuclei to the other side of the nuclei. It's either here or there. So in this case, it's better. And here you have, as usual, the states. Now, when we do this, and we want to describe one electron potential to describe the atom, usually what we do, we fit these parameters such, this, and this, such that this energy will be the ionization energy of the ground state of our atom. And then we take another state. We have two parameters, so we have ability to fit two eigenvalues. And we fit it such that this will be the ionization energy. This will be now the ionization energy of the ground state. This will be the ionization. This will be the ionization energy of the excited state. You are with me? Good. What's happened to this? So depends on the sign, but it doesn't matter for us. This apply something like this. In our case, this would not Z, it will be X. So now we take it to this. We add to this plus epsilon 0. In atomic units, this is 1. And here we put it to be X, plus or minus. So if you take this, this is the minus sign. So now our potential look like this. And this will oscillate. And this is oscillates even faster. There is no threshold here, really. Most of them will be resonance metastable states. So here the shape is a barrier induced by the static field. And it's interesting to note, sorry, here, it's come to be, I'll do it again here. It will become to be like this. It's the potential, if this is the threshold. So, I'm sorry. Yes, this will be like this. Now, if you take, as an example, the potential to be like this, and now you apply a static field, and then because you apply a static field, it's come to be like this. We apply the static field. This is infinity. This will become to be, let's put it like this. It will be easier for me to do it like this. Then we add something like this. So we take a quantum well and we apply a static field. Then it comes to be such a potential. Agree, Nitzan? Yeah. So again, we have states which are turning here. These are resonances. But because of what I said, you will see also very broad resonances here. The amplitude outside will be large. They will be less localized here than this. This will be very strongly localized here. This will be lesser. But there is a surprise here. If you take this static field epsilon 0 to be large enough, you will get additional new type of metastable states. What are? Somebody can guess where they will be located? They will be located here. Strong localization. Remember what I said. This is a sharp, abruptly change in the potential. If the change is large and this is low enough, remember what I proved to you, it's to get even bound states at the continuum, if this will go to infinity. So what you get here, new resonances, very long-lived, namely to have the amplitude here is much larger than the amplitude outside. Mode even can be more than this. It depends on the parameters potential and the potential parameters. So again, these are the tunneling resonances as we are used to because of the DC field. And these are not really related to tunneling, but it's shape-type resonances, very broad, hard maybe to see. But then if the depth of the well is large enough and the DC field is strong enough, you will pop out metastable states, resonances, that are localized in space, not in the well, here. And in time, these electrons will get through and will tunnel from the quantum well. And before taking a break of 5 minutes, I want to say that this type of resonances, which I showed you here, they like associated with the DC field, it's can be used to describe leaking modes from or in bended waveguides. So I want to say something about this. So let's put here a line. So now I want to tell you how this is really related and describe phenomena in nature which is in optics. And I do it because it's very interesting that the Maxwell equation under some circumstances looks very similar to the Schrödinger equation. And when it's happened, when you understand and study phenomena in atoms in DC or AC fields, whatever, or molecules, you take this mathematical understanding that you have, the implicit derivation, and use this understanding, transform the equation from being to be Schrödinger to Maxwell. If the mathematics looks the same, then you end up with understanding of new phenomena in the other field. And sometimes it will be breakthrough. It will be a big surprise. And I think that I mentioned, at least to my students in the group, that many years ago, with one of my students at that time, Ilya Verubeychik, with somebody from electrical engineering, Meir Ornstein, we established a startup that produced optical switches based on the understanding that we had in our group on phenomena which are associated with the interaction of electrons in atoms with external laser field. It looks like not related, but the mathematics is exactly the same as solving the Maxwell equation for waveguides. So I will not describe this now, but I want to emphasize how breakthrough can happen when somebody moves from one field to another. And actually, in this startup, we developed a device that, as I know now from my student who is in the United States for years already, that their devices that they implement it in different materials, and they sell it for millions of dollars per year. One of my students say $30 million per year, another one says $50 million a year. I get zero, so it's not important. So how comes this is not the subject of this talk? But it turned out to be success. And so coming to say what it is. So if you use the scalar Maxwell equation under a paraxial approximation, you end up with a solution if you have a waveguide. And here I plot x, and here the index refraction as function of x. And the index of refraction is large here, so call it n1. And here it's n0. This is the index of refraction of the cladding. The light, the local modes are here. And how I can see it immediately. You see, when I do it like this, you know, maybe you need to do Snell rules or something to think about something. How I see it immediately, that this is the situation. Because when I look at the Maxwell equation, the scalar Maxwell equation, which is solved, it's look like this. It's I put it a partial derivative. Also, it's in this case, it's like this, plus 2 pi over lambda. This is the wavelength of the light in vacuum, square, n square x. And this is the amplitude of the field inside this material. This is the electric field, and this is the amplitude of the electric field, and this is the propagation constant. The z direction is z. This is the z direction. And if you solve it properly, you will see that these solutions should be multiple by E plus or minus I beta z. This phase factor, say the propagation constant along the z direction. So it really looks like the time-dependent stationary solution in the time-dependent Schrödinger equation, is it? And plus is the propagation along this direction, and minus along this direction. And it's interesting, this is not now the subject to discuss, that even if you take the index of refraction to be slowly varied along the z direction, you can still use a similar equation, but not for DC field, for AC field. But the point that I want to make, that the reason that you don't get actually simple reflections here from here to here, when you do the analog of the Maxwell reflection to the Schrödinger equation with the paraxial approximation, you neglect the reflections. It's only always, if you start with plus, it always go plus, never will return. In this case, it's clear because the index of refraction is invariant along the z direction. So I said too much, but if you look at this, you see something interesting, that if I change the sign, this comes to be Hamiltonian. This has come to be the time-independent Schroeder equation. Anyhow, this is the story. Now, why am I coming to be like this? It's now it's clear that if you take this potential that I put it here, this potential in our case is now minus 2 pi over lambda square n x square. This is the height of this potential. Now, what's happened if we take a straight waveguide like this and we bend it? So we bend it such that it will go now to be like this. So this is x, this is z, this is y. So we bend it here with a radius r to some point. It's possible to show, and I'm not showing you, that you effectively can define new, you can solve the, now instead of solving this one, you can add to this now. You add here minus some, call it parameter A. R is this radius, and here will be x. So this parameter is related to the angle that we bend it. And because of this, what we expect to have, like here, if you take it to be, we expect to have leaking modes. These modes that was before here, these are the trapped modes in the optical waveguides. You can design such that you have only one. You can design it such that they have two multi-modes. Can you design it such a well, symmetric well, that you don't have any trapped mode, bound state? The answer is no. You can prove that any well, it doesn't have to be rectangular. When the thresholds in the left and the right are identical, always you have at least one bound state. So whatever you do in this symmetric waveguides, it doesn't matter how it looks, always you have one bound trapped mode. But in the moment that you bend it, you get all of them come to be leaking modes. The question is, what is the rate of decay? How you can prove it? Go to the lab of your friends, take an optical fiber, and bend it. And the moment that it's bended, you'll see that the light will escape out of the waveguide, or the optical fiber. In waveguides, you need to do in the lab, but optical fiber, go to any physical chemistry or physics lab, they have optical fibers, take the optical fiber, ask them to transfer light through the fiber, bend it, it will escape. This is why when they bended the optical fibers or waveguides, they need a lot of territory. It's like in the highways, you know, you need to make a very large loops. Now, in order to read about it and even how to reduce the territory and how you can make sharp bending without having leaking mode, you should look at the thesis of Yoav Berlatsky that did his PhD thesis. Look at his PhD thesis. He did it at the Technion in physics. Actually, he worked in the beginning in our startup, and then he did a PhD on this subject. And just for curiosity, and then I will make the full stop of this part of the talk in order to be more alive, to say that he did his master actually, but he did such mathematical brilliant work that the committee decided to give him PhD on master thesis. So this is the only example that I had in my career, at least in the Technion, that somebody did master and got PhD. So if people want to learn more specifically how it's happened and how to do this and how to make the bending such that the modes will not trapped and to increase their lifetime and to make the territory to be smaller, go read this thesis. Okay? 5 minutes break, okay? Now we will continue to talk about other type of resonances, Feshbach resonances. But before doing it, I want to address myself to the comments that I heard during the break. The first comment was here, תודה רבה ניצן, to say that before the propagation axis was the z direction. When we have a leaking mode, we see from this picture, and when we apply this, that the light will escape not necessarily to along the z direction. The propagation is actually in the direction of, in the plane of z and y, when you see it here. And x. And so actually, really, when we solve it, and when you look at the Berlatsky paper, it's solved in the three-dimensional picture. And when you do it like this, it's actually in 2 dimensions. It's in x and y, actually. And you should look at the physics to see how it's happened, like this. And these coefficients that I put here, well, I erased it before. Here I erased it. The new term that is coming, this term, this A, it also depends on the mode that we become to be leaking mode. So it's come to be more complicated, but roughly speaking, it's what I told you. Another comment that I had is, can we use the similarity between the Maxwell equation in the paraxial approximation, which is scalar Maxwell equation, which I didn't tell you what is the Maxwell paraxial approximation, but because it makes it to be looks like the Maxwell equation to be like the time-dependent Schroeder equation when z is time. And for Hebrew, I usually like to say it's easy to understand because time in Hebrew is zman, and zman is z. So if you write the Schroeder equation in Hebrew, instead of t, you will write z, and then it's clear that this is the propagation axis. And then the question was, can you use this as an advantage, namely to study basic phenomena in matter waves from wave mechanics, do experiments in optics, and learn about phenomena in quantum mechanics? The answer is sure. This is the beauty in quantum optics. And here at the Technion, we have the lab of Moti Segev. This is what he is doing for his living with his students. And if you look at and see how many natures and science and physics of letters, etc., are coming from this group, you understand the impact that they make on the community, because sometimes there are phenomena that it's hardly to measure and see clearly how they appear in quantum mechanics. But it's come to be very clear in wave mechanics. In particular, without giving examples, look at this site and then see the examples, but without doing all these examples, in principle, it's clear. In quantum mechanics, the wave function, the matter waves, is only in our imagination. Nobody can really measure the wave function, the amplitude. Maybe they can somehow measure the probability density, or quantities that are calculated by using this wave function. But the wave function itself, with all this complexity, cannot be really measured as it is in quantum mechanics. Actually, this is the whole idea of the collapse phenomena, that the moment you do the measurement itself destroys this matter waves behavior, and you collapse now to classical quantities. But in optics, you can take pictures of it. You can photo the wave function. So this is big advantage that have us in hints about to understand what happened in quantum mechanics. About the similarities, what also here, Anael, you asked about learn about molecules from optics. This is more difficult, not only in atoms but other phenomena. And the reason is because that in quantum mechanics, in particular, if you take molecules, you have many body problem, and you have also interaction among the electrons, electronic repulsion. You have, for example, a phenomena like Auger, that I'll describe it to you in this discussion. It's a Feshbach type example for Feshbach phenomena, that you have bound states embedded in the continuum, and because of this, you have ionization. Because of the electronic repulsion. If you don't have the electronic repulsion, you will not have this phenomena. Maybe I'll start with this example because of this comment. So in optics, in a way, it's one body problem, and we cannot have this in a simple way, any way to describe the repulsion between electrons. Also, the Coulombic potential is long-range potential. These are short-range potentials. So there are differences, of course. But still, you can do a lot. And I have to say that, because I mentioned the group of Moiseyev, that because of our interaction on non-Hermitian quantum mechanics during the last years, if you look at the papers, many phenomena that we talk about non-Hermitian quantum mechanics, they were measured for the first time in optics. And nice enough by Moti and Dimitri from Florida, they actually made a breakthrough in optics because of using this non-Hermitian quantum mechanics and standard quantum mechanics, of course. So because of what I said about this phenomena that how to describe optics, I will start with it.